Hello friends, welcome to the mass transfer phenomena in the polymeric systems under the edges of polymer process engineering. So dear friends, in this particular segment we are going to discuss about the mass transfer operation, then we will discuss about the mechanism of mass transfer, then the molecular diffusion, we will discuss about the Fick's law of molecular diffusion, then diffusion velocities, unsteady state diffusion, the steady state diffusion through the constant area. Then we will discuss about the Fick's second law of diffusion for polymers. Now, there are three most, you can say, the central topic in chemical engineering, and they are equally applicable in the polymeric system. Like one is the synthesis of material. For any raw material, we need to process them and to make the finished product for our commodity use or day-to-day use or for the different industrial or specialized use. So, once you are having the specified quantity and a specification of the raw material, then there is a process, and this process converts all these raw material into the useful product. Then second one is the remediation of the polluted air, water and soil. The industrial revolution and the day-to-day activities led to the pollution of the environment, and we need to have a remediation of these three forms of the material exist on the earth. Next is the energy generation. Now, separation of the chemical mixtures into their constituent is being practiced for long time. The reason is that because sometimes you cannot have 100% conversion. So, if you are having a reaction mass, then there may be some unreacted component, there may be some byproduct, there may be some product which are desired. So, you need to separate all those things. Apart from this, nature has given so many things, and you need to separate all those useful things from that particular segment. It is again under the edges of the separation of the chemical mixture. Now, there are various verticals for these separation protocol. One is the extraction of the metal from ores like perfume, from the flowers and the dyes from plant, then evaporation of the seawater to generate the salt, the production of distilled liquid through the separation process. All these are the example of the separation process. Now, in chemical industries, there are chemical reactors and then separators. So, the chemical reactors, they are the central feature, but in terms of the cost, the separation cost dominates over the chemical reactors, because ultimately our main intention is to get the useful product in a purified form, or the form which is described as per the specification. You need to get it, and that is why when it separates it out, it added to the cost of the product. The separation cost is directly dependent on the final to the initial concentration of this substance. So, for this the ratio is large and the product cost is large. For example, the pure uranium cost is much higher because in nature it found is much less quantity in a lower concentration. So, to purify and to produce a pure product it involves a huge separation cost, whereas the production of the sulfuric acid is much cheaper. Now, there are various separation protocols which are based on either entirely the separation of different particles, grids or different particle sizes, usually maybe by the screening, maybe by other separation protocols, or the filtration of the solid from the suspension of the liquid. Now, let us talk about the mass transfer. The mass transfer is net movement of component in a mixture from one location to another location in the presence of a difference in the concentration or a partial pressure, because some driving force must be there. One example is that lump of sugar added to a cup of water, which dissolves and then diffuses throughout the cup uniformly. Another example is to deliberate use of agarbatti. The fragrance generally spread uniformly, and when we put agarbatti at home. So, if you light the agarbatti at one corner, over the period of time the perfume or the fragrance it approaches to the all corners, and you may say that all these fragrance distributed throughout the area in question. Then drying of cloths under the sun. The drying occurs because the moisture diffuses into the air. So, these are some of the driving forces. Then let us classify the mass transfer operation. As we know that the three stage of matter, gas, liquid and solid. So, the combination of these three states can form three different phases of possibilities of phase of contact. One is the gas-gas system, the two different gases, gas 1 and gas 2. Two different gases, if we keep them in a two container and allow them to mix, they will uniformly mix by the process of diffusion. Then the gas liquid type of a system, absorption. Usually it is one of the such example, like here you are having the gas liquid and disperser, one disperser is there. So one of the such example of a gas liquid system, this suppose a solute is changing from a gas phase to the liquid phase and two mixture of ammonia and air, let us say that ammonia and air. We have water in the liquid phase. So, ammonia will dissolve, this is the ammonia, ammonia will dissolve in water and form the ammonium hydroxide, and air does not dissolve in the liquid. So, in this case, there is an interface between the gas and liquid, and one component of the gas phase preferentially dissolved in the liquid phase from the solution, and this is known as absorption process. Another thing is the distillation. Now here the salient feature, like you are introducing the feed over here, this is the refluxes and this is the reboiler section, and so we have a reboiler here where we heat the liquid and it forms a vapor phase, and liquid is fed from top as a reflux and it comes down like this, and there is an intimate contact of between the gas and liquid. So, when there is a difference in their boiling point among the mixture or the component, then we can create the two phases, the vapor phase and another liquid phase, and vapor phase will be mostly on the lighter component and the liquid phase will be on the heavier component. Therefore, we can separate the two different components or multiple component, and this process is known as distillation. Another segment is called the drying. This is a type of a gas solid system. Now here this is a typical dryer, and you see the dry material, this fluidized by chamber. So some sort of a driving force are there. Then adsorption is a very common phenomena over the surface. This is a sample surface. Over this the adsorbate is being accumulated over the period of time. Then the liquid system. The prominent segment is the extraction. So, when we talk about the liquid system, the crystallization, the process of formation of the solid from the liquid solution based on the difference in the solute concentration and its solubility at a certain temperature. Then the leaching. This is a selective dissolution of a component from a solid particle by a liquid solvent. This is known as leaching. The example is the formation of some medicinal component from the plants. Now, usually when we talk about the mechanism of mass transfer operation, so usually it occurs by two basic mechanisms. One is the molecular mass transfer, the molecular diffusion by random and spontaneous microscopic movement of individual molecule in a gas, liquid or solid as a result of the thermal motion, which is known as the molecular mass transfer. Then the convective mass transfer. In this case, the ED diffusion by the random macroscopic fluid motion is the responsible function for the convective mass transfer. Here you see that. What are the driving force for mass transfer for operation? You see, when we the agarbatti at one corner and it goes to the other part, then there must be some driving force. So let us talk about those driving force for this mass transfer operation. One is the two-phase system. The spontaneous alteration through the molecular diffusion occurs in air-ammonia mixture. The ammonia diffuses to the liquid and spontaneous alteration of the molecular diffusion occurs, and ultimately the system comes into a state of equilibrium where the alteration stops. Another is the multi-phase system. It deals with the diffusion process in each phase separately, and the mass transfer in one phase. The concentration is the driving force. Where there is a multiple phase, the true driving force for the mass transfer is the chemical potential. Let's talk about the molecular diffusion. The molecular diffusion is defined by the movement of individual molecules through the substance by virtue of their thermal energy. Now, this can be explained by the simple kinetic theory. Now, consider the two different type of molecules, molecule A and molecule B. A molecule is imagined to travel in a straight path at a uniform velocity until it collides with another molecule, whereupon its velocity change in both the directions as well as the magnitude. So, this is A and it collides with B. Now, the net distance or the average distance of the molecule travel between the two collisions is known as the mean free path here. The molecule travels through a highly zigzag path. The net distance travel in one direction in a given time is defines as the rate of a diffusion. So, the rate of molecular diffusion is very slow, and the rate of diffusion can be increased by reducing the pressure. When we reduce the pressure, then this reduces the number of collision, and this can be increased by the increasing temperature. When this increases the molecular velocity. Now, let's talk about the effect of barrier on the molecular diffusion. Let's take a system where we have a water and on a reservoir, and it is a vacuum above heat. So, the rate of evaporation of water at say 25 degrees Celsius into the complete vacuum is quite high, which is around 3.3 kilogram per centimeter per square meter of water surface. Now, if we place a small layer on top of this water surface of a thickness say 0.1 mm, the rate of diffusion will reduce by a factor of say about 600. This shows the barrier has an immense importance on the molecular diffusion. Let's talk about the mass concentration. The mass concentration of the component is given by the rho I is equal to mi over v, and some of the mass fractions can be given as summation of I is equal to 1 to n wi. This can be the summation of I to n rho I over rho, that must be equal to 1, and the total mass concentration can be given as rho is equal to summation of I to n rho I, and the mass fraction is wi is equal to rho I over summation of I to n rho I. Another component in question is that molar concentration of component I, that is Ci is equal to Pi over RT, and the total molar concentration can be represented as C is equal to summation of I to n Ci, and the total molar concentration of ideal gas mixture can be given or can be mathematically represented by this particular formula. C is equal to 1 over RT, summation of I to n Pi is equal to Pt over RT, and the mole fraction of component I, that is very common in the liquid or solid, that can be given as Xi is equal to Ci over C, and the mole fraction of component I in the ideal gas mixture, this can be given as Yi is equal to Pi over Pt, that is the total pressure, and the mole fraction of the component I in gases can be given in terms of the concentration, and that is Yi is equal to Ci over C. So, if we talk about the sum of the mole fraction, that is the summation I is equal to Xi is equal to 1, and Yi summation Yi is equal to 1. Now, let us take up one question, that is the feed to an absorber has the following composition at 313 Kelvin and 200 kilopascal, that's per the given the figure, like 90% of methane, then 5% C2H6, 4% of NC3H8 and 1% of NC4H10, and you need to calculate the composition of the feed gas in terms of the mass fraction and the total concentration in the feed gas. Now, for this we need to take the basis 100 kilomole of feed gas mixture. Now, here we have given the components CH4, C2H6 and C3H8, butane, and which is total 100, and the molecular weight and the mass in kilogram or kilomole the molecular weight, and the mass fraction is given like this because we have calculated the total one. So, the molar concentration, total molar concentration C, the C is equal to Pi over RT, and this 200 is given 8.314 into 313, and that comes out to be 0.077 kilomole per meter cube. So, average molecular weight M average is equal to 1824 over 100, and that comes out to be 18.24 kilogram per kilomole. So, the total mass concentration rho is given by Cm average, which is 0.077 kilomole per meter cube into 18.24 kilogram per kilomole, which comes out to be 1.40 in per meter cube, and this is our answer. Now, let us talk about the diffusion and velocity. The mass average velocity is defined as the mass concentration, which can be represented as this particular mathematical relationship, where Vi is equal to absolute velocity of a species I with respect to a fixed reference frame, and omega I is equal to mass fraction of a species I. So, this is the V mass average is summation of I to n rho I Vi over summation P rho I, and that is equal to summation I to n rho I over rho into Vi, and this is the summation I is equal to 1 to n omega I into Vi. If we talk about the diffusion velocity, then the molar average velocity is very important, and it is sometimes defined as in terms of a molar concentration. So, which can be represented like this, where Xi, this is slightly different from the previous formula. Here Xi is the mole fraction of species I. Rather, here we use this omega I, which is the mass fraction of species I. Now, let us take up another question, that is a gas mixture. This contains about 15% of hydrogen, 30% of carbon monoxide, and 5% of CO2, and remaining is nitrogen. This flow through a tube of say 1 inch diameter and 15 bar the total pressure. If the velocities of the respective component, they are 0.05 meter per second and 0.03 meter per second and 0.02 meter per second respectively, you need to calculate the mass average and molar average velocities of the mixture. Now, let us rename the gas mixture as H2 is equal to H2 CO2 CO2 3 and N2 4. So, the molar average velocities can be given as per the formula 1 over C, C1 V1 plus C2 V2 plus C3 V3 plus C4 V4, and that comes out to be Y1 V1 plus Y2 V2 plus Y3 V3 plus Y4 V4, where Y is the mole fraction of component I in the gas mixture. So, if we put the values, then V can be given as 0.15 into 0.05 plus 0.3 into 0.03 plus 0.05 into 0.02 plus 0.5 into 0.03, and this comes out to be 0.0325 meter per second. So, the mass average velocity, the mass average velocity is given by V mass average, which is equal to rho into rho 1 V1 plus rho 2 V2 plus rho 3 V3 plus rho 4 V4, and rho I is equal to Pi m I over RT, and rho is equal to P m average over RT. So rho I over rho is equal to Pi mi over P m average, which is equal to yi mi over m average, where rho I is the mass density of ith component, rho is the total mass density, mi is the molecular weight of ith component, and m average is the average molecular weight of the mixture. Now, if we put all the values, so m average is equal to yi m1 plus y2 m2 plus y3 m3 plus y4 m4, and if we substitute the value 0.15 into 2 plus 0.3 into 28 and so on, this comes out to be 24.9. So if we calculate V mass average, that is 1 over 1 over m, that is summation of I is equal to 1 to n is equal to 4, because, and yi m I v I. So if we substitute the value of V mass average, which is comes out to be, if we substitute all the values given, then it comes out to be 0.15 into 2, 0.505 plus 0.03 into 28 into 0.03 and so on. This comes out to be Vm mass average comes out to be 0.14 meter per second, and that is our answer. Let's talk about the fluxes. Now, flux is defined as the rate of transport of species I through the unit area normal to the transport. Now, the flux of a given species is a vector quantity. Flux may be calculated with respect to the coordinates fixed in space or coordinates moving with mass or molar average velocity. Now, mass flux, this is calculated with respect to the coordinate fixed in space or relative to stationary observer. So, this can be represented by this formula, that is the mass flux Ni mass is equal to rho I into Vi. The total mass flux N mass is equal to rho V mass average. Now, the calculated with respect to the mass average velocity or relative to an observer moving with the mass average velocity, and that can be the mass flux, that is Ji mass is equal to rho I into Vi minus V mass average, and the molar flux, this is calculated with respect to the fixed phase or relative to stationary observer. So, the molar flux is equal to N molar, that is CIVI, then total molar flux, that is N mole, is equal to CV molar average. Now, this calculated with respect to the average velocity or the relative to an observer moving with the mass average velocity. So, the molar flux Ji, this can be represented at CIVI minus V mole average. Now, let us talk about the relations between the fluxes. So, this can be Ji mass is equal to rho I Vi minus V mass average, and Ni mass is equal to rho I Vi, and Ji mass is equal to rho I into Ni mass over rho I minus rho I V mass average. So, the Ni mass is equal to Ji mass plus rho I V mass average, and this comes out to be Ji mass plus rho I N mass over rho. So this is my first formula. Similarly, we can write Ni mole is equal to Ji mole plus Civ mole average, and this comes out to be J ith component plus Ci over C n mole. So this is our next one. Now let's talk about the Fick's law of molecular diffusion. Now Fick, the Adolf Eugene Fick's, a German physiologist, he has given a law for the diffusion of a component. The Fick's first law defines the diffusion flux of a component A in an isothermal isobaric binary system and proportional to the concentration gradient in a particular direction. For diffusion of a component A in x direction is given by Jax is equal to minus Dab dCA over dx, where Ja, this is the molar flux of component A in x direction. The unit is having the amount of material diffused over n square time, and then this Dab is the diffusion coefficient and Ca is the concentration of A. Now, the relationship between the mutual diffusivity of species A and B, this can be given by, say, Na is equal to Ja plus Ca over Cn. This is equation number 1. And for gas mixture, Ca over C is equal to Ya, and Ja can be represented as minus Dab dCA over dx. So if we put the values in the equation 1, we get Na is equal to minus Dab dCA over dx plus Yan. This is our equation 2. Also, dCA over dx is equal to C dya over dx. So therefore, the equation 2 becomes, this equation can become Na is equal to minus C dAb dya over dx plus Yan. This is our equation number 3. Similarly, Nb is equal to minus C dBa dyb over dx plus ybn. This is equation number 4. Now, if we sum these two equation 3 and 4, we get Na plus Nb, that is comes out to be minus C dAb dya over dx plus Yan minus C dBa dyb over dx plus ybn, or minus C dAb dya dx minus C dBa dyb over dx plus Ya plus ybn. Now, since for two components Na plus Nb is equal to n, Ya plus Yb is equal to 1. So, dya over dx plus dyb over dx is equal to 0, and dya over dx is equal to minus dyb over dx. Therefore, n is equal to minus C dAb dya over dx plus C dBa dyb over dx plus 1 into n. Hence, dAb is equal to dBa. Now, let us talk about the unsteady state diffusion. So, let us consider unsteady state diffusion in this particular case. Let us consider the point M here and a point N. The change in the concentration of a component of the diffusive constituent in a mixture over a time is unsteady state diffusion, and the balance equation can be given as N generation is equal to out plus accumulation. So, the mass flow rate of the component A can be given this particular equation, where Nax is the flux in the x direction, and this one is the value of the flux at some location x, and Ma is the molecular weight of A. So, the generation of A by the chemical reaction. Now, let us the rate of the chemical reaction be Ra is equal to mole per volume into time, and the rate of generation of the product can be given by this particular as a mathematical representation, and mass flow rate of the component A out can be represented by this, and the rate of accumulation which can be represented in the delta form, like where rho A is the density of component A. Now, if we put all the values in the balance equation, then it can become the Ma into Na x plus delta x minus Na x delta y delta z plus Nay x plus delta x minus Nay x delta z plus Naz x plus delta x minus Naz x delta y plus delta x delta y delta x del rho A over del t, and that is equal to MARA delta x delta y delta z. Now, if you divide both the side by delta x delta y delta z, and if we take this delta x tends to 0, delta y tends to 0, and delta z tends to 0. So, for we have the component for component A, that is Ma del Na x over del x plus and so on, plus delta del over rho A over del t is equal to MARA. This can be equation number 5. And if similarly we can write for the component B, and that can be represented as MB RB or MB del NB x over del x plus and so on. This can be equation 6. Now, if the total material balance after adding equation 5 and equation 6 can be represented by MARA plus MBRB. Now, if we take the rho is equal to rho A plus rho B, that is the solution density. In that case, MA RA plus MB RB must be equal to 0. So, if we substitute to this all these things, it can become the equation number 7. Since the mass rate of generation A and B must be equal to 0, so Vx is equal to rho A Vax plus rho B Vbx over rho A plus rho B, or rho Vx is equal to rho A Vax plus rho B Vbx. So, rho Vx equal to Ma CaVax plus Mb Cb Vbx, and which is equal to MaNax plus Mb Nbx, where Vx is the mass average velocity, Vax is the absolute velocity, and Nax is the molar flux. So, if we substitute, so it can become Ma Na plus Mb Nb over del x is equal to del Vx over del x plus Vx del over rho del x. This is equation number 8. So, if we substitute equation 8 into equation 7, we get del Vx over del x plus del Vy over del y plus del Vz over del z plus Vx del rho del x plus Vy del rho over del y plus Vz del rho del z plus d rho d del d Q, this is equal to 0. This is equation number 9. Now, this is the equation of continuity or the mass balance for total substance. Now, if solution density is constant, then equation 9 we have del Vx over del x plus del Vy is del y plus del Vz del z is equal to 0. This is equation number 10. So, we know that in terms of mass flux and in the x direction, Nax is equal to Nxa plus Jax. Now, if we substitute the value of and if we put on all those things, then it becomes Nax is equal to Nxa plus Mazax, or Nax is equal to Macvx Ca over C plus Mazax, and this comes out to be Ma del Nax over del x is equal to Vx del rho A over del x plus rho A del Va over del x plus Ma del Jax plus del x, and this is Vx del rho A over del x plus rho A del Vx over del x plus minus Ma dAb del 2Ca over del x2. Then equation 5 becomes Vx del rho A del x and so on plus rho A del Vx over del x plus del Vy over del y plus del Vz del z minus Ma dAb del 2Ca over del x2 plus del 2Ca over del y2 plus del Ca over del z2 plus del rho A over del t is equal to MARA. This is the equation number 11. Now, when rho is constant, so if we use the equation 10 and dividing Ma in equation 11, this can become V del Ca over del x plus Vy del Ca over del y plus Vz del Ca over del z plus del Ca over del t, which is equal to dAb del 2Ca over del x2 plus del 2Ca over del y2 plus del 2Ca over del z2 plus Ra. This can become the equation 12. So, in a special case where the velocity equal to the 0 and no chemical reaction occurs, so from equation 12 we get del Ca over del theta is equal to dAb del 2Ca over del x2 plus del 2Ca over del y2 plus del 2Ca over del z2, and this is the Fick'second law. It is frequently applicable to the diffusion in solid and to limited situation in fluids. So, dear friends, in this particular segment, we discussed about the various mass transfer segments and operation which are useful in the polymer processing. And for your convenience, we have been listed several references which you can utilize. Thank you very much.